let's now discuss David Huffman's alternate and better approach. So what's interesting about it is that it is kind of the only other obvious way to do coding. That is, Shannon and Fano did what is sort of a top-down approach, and Huffman's is just the bottom-up version of the same. So let's just walk through it, and then we'll reflect a little bit on what we have at the end. So Huffman does the exact same thing as Shannon and Fano, and that he counts each of the characters and says, well, 35% of them are this character, 16% are this one, and so forth. He then creates a node for each character, and it gives that node a weight corresponding to its relative frequency. We then take the two nodes of minimum frequency, and we combine them into a supernode that has weight equal to the sum of the weights of the original two. So here the 16 and 15 are merged into a single supernode, so to speak, of weight 0.31. So what's next? We have four nodes. So which two have the smallest? The 0.17s. So we merge those together and we get a node of 0.34. Now which two are the smallest? The 0.34 and the 0.31. Okay, so we merge those and we get a single supernode of 0.65. And then lastly, we have two nodes. We combine those together. And now we have a tree, which where the supernode at the very top has weight 1, which will always happen. Now the way we get a code out of this is that for every left link in the formation process I described, we give that a 0, and on the right we have a 1. And so ultimately what we end up with is a code where this very common character has only one digit representing it, a 0, and then the prefix-free code for the other four characters is, well, as shown. So this approach, it's very intuitive, very simple, and yet it took Huffman many, many months of serious thought to come up with this idea and to prove that it is correct. So often really beautiful ideas, they could be hard to find, even though they could be easy to appreciate. So question for you to see if this all really makes sense. What I'd like you to do now is figure out if we use a Huffman code to encode some text, how many bits per symbol do we need? So I've given you 3 possible answers, 2.6 bits per symbol, 2.3, or we don't have enough information. So here is the relative frequency of each character, and here's the Huffman code. Try and give that problem a shot. Okay, so it turns out the correct answer is 2.3 bits per symbol. And you can think about this two ways. One is using intuition, kind of looking at this and feeling out exactly what's going on. But if that doesn't do it for you, another approach is to say, well, let's imagine we have a text with 100 symbols. Well, by definition, 35% of those characters are this one. So there's 35 of those. There's 17 of these, 17, 16, and 15 of these. And if we want to count up the total bits, well, that would be 1 bit for every one of these characters. That would be 35 bits. That would be 3 bits for all of these. And so in total, we add up the total number of bits for all characters. We would get 230 bits, and we divide that by the number of symbols, which is 100, and we get 2.3 bits per symbol. Okay, so that's the amount we have to pay. Now I'd like to note that that is smaller than, say, the 8 bits per character that we have to pay to represent English text using ASCII. So to that point, let's imagine that we have a file that has 350 of this character, 170 of this, 170 of this, and so forth. How many total bits would we need to encode this file if we were using what's known as 32-bit Unicode? So what's that? Well, as we said earlier, English text is often represented as 8 bits per character, but with Chinese, we need a bigger character set because that's not enough bits. 8 bits is not enough. So instead, typically, we'd use what's known as 32-bit Unicode, so that each of these characters takes 32 bits to represent. So think about how many total bits we need to represent this file in 32-bit Unicode, and what would it take with our Huffman code? You don't need a calculator for this, and this is just to make sure that we understand how Huffman coding helps us. Okay. So here we have a total of 1,000 characters. So if we're using 32-bit Unicode, it's going to be 32,000 bits. Okay. If we use our Huffman code, well, we just said it was 2.3 bits per symbol, or per character, equivalently. So that would be 2,300 bits. And so what we see is that this code is 14 times as efficient. That is, if we're using the Huffman code rather than Unicode, we only need 1/14 the size. And so if we are compressing, say, Moby Dick using a technique like this, That's how we're able to compress things down and then expand them back later. And we're taking advantage in some sense of the pattern of the symbols. So our code, as we've seen, is 14 times as space efficient, though there's a downside, which is that our new code can only encode strings that have these 5 symbols. If we have another character, say an English character or any other Chinese character, we'll have no way to represent it. Our code only supports these 5 characters. So that's the trade-off. We get more efficiency because of the fact that we're only representing a subset of all possible characters. Okay? So that's the basic idea behind Huffman coding. So then to compare Huffman and Shannon-Fano codes, we can actually look at them side by side. I didn't say it before, but the Shannon-Fano code, you can work out the math, is 2.31 bits per symbol, whereas the Huffman code is only 2.3 bits per symbol. And so ultimately, we can see that the Huffman code, it is better. Like this code we get out of it, or sorry, with this code we get out of the Huffman encoding process, it is literally better in every possible way. There's no downside to using Huffman coding, and so this is now an obsolete technology. Hence the fact that it is an extra slide. Just a bit of a historical note.